Hello everyone. Title of this video is Rk4, which stands for is Runge-Kutta 4, meaning 4th order. Sometimes the Rk4 method is called the classical 4th order Runge-Kutta method. And this is, in several examples here, this is a method like the improved Euler's method and regular Euler's method. It's a method used to approximate the value of a solution to an initial value problem at some given input. All right. So we're given a first order differential equation with some initial condition, right, some point that the solution curve passes through, and then we use a certain, some method, the Euler, you've seen, I've put out previous videos on Euler's method, improved Euler's method, and now here's another method where we're going to start at that initial condition, start at that initial point, and starting from there, using some sort of recursion formula, end up approximating the value of the solution curve at some other point, right, at some other input. All right, now Euler's method and improved Euler's method used the first derivatives, used the slope field, traveling kind of traveling on from the initial point through the slope field to get to some other point on the coordinate plane that was, relatively close to the actual solution curve. The Runge-Kutta methods use Taylor polynomials. So I'm not going to go into the development of the method. All right, I'm just going to use it. If you please, hopefully you've read your section, whatever book you're looking at, on the development of the Runge-Kutta methods. When they say 4th order, it means the parameters were chosen to fit a 4th order Taylor polynomial approximation to a solution curve as best as possible. And also please know that this Rk4 method I'm going over is just one example of a 4th order Runge-Kutta procedure, Runge-Kutta method. It's just used so often that it's given a special name, Rk4. Classical. Alright, so enough of this, let's get into it. Alright, so here I have the recursion. It's pretty involved and is very, very daunting to do by hand, especially if there's more than one step involved. So what I'm going to do here, I'll go over the recursion here with you. Then I'll go into an example, and I'm going to show you how one step is performed by hand, possibly two. And then you'll see after this 1 or 2 steps I perform by hand how incredibly tedious this would be if you have to do 5 steps, 10 steps, whatever. And I'll show you instead a website I found that does Rk4 method calculations for you, which I would highly recommend instead of doing the tedium by hand. Anyway, so the recursion formula used for Runge-Kutta 4, Rk4, so the n plus first y coordinate, ym plus 1, equals the nth y sub n, plus h divided by 6. Now remember, h was the step size. Right, you start at some value x sub 0, and then you keep adding this h to get to new x coordinates. So it's a change in x. So y sub n plus h divided by 6 times this quantity here, where you have k1 plus 2k2 plus 2k3 plus k4, all in the parentheses. where these k values are found the following way. K1 is the value of f at xn, yn. Now this f is just what, when you're given the initial value problem, the differential equation is going to look like y, it's a first order, y prime equals some function of x and y. That's the f. So K1 is f at xn, yn, the previous x and previous y. K2 is f at xn plus half h for the x coordinate, the new x coordinate there, comma yn plus half h times k1, whatever k1 was, for the y coordinate. Right. K3 is the same thing, but instead here you have k2. It's f of xn plus half h, comma yn plus half h times k2. And then K4 is f of xn plus h, yn plus h times k3. So I do have to find these then in this order, because you need K1 to find K2, you need K2 to find K3, you need K3 to find K4, and then you need all these to find the next y coordinate down. Alright. So as you can see already, pretty involved. Let me just show you at least the use of this one time, and then I'll go to show you an online calculator for Rk4. Alright, so first example. Now this is an example I've used in the past couple videos as well, on improved Euler's method and also regular Euler's method. Now I'm using the same initial value problem. I'm asked to approximate the same output, y at 1.5, but this time using this Runge-Kutta method, Rk4 method. And I have specified specifically, with h equals 0.1, right? So a step of 1/10 every single time. So we're asked to use the Rk4 method with h equals 0.1 to obtain a 4 decimal approximation of the indicated value. Alright, so here's the initial value problem. We have y prime equals 2x minus 3y plus 1. Alright, so this 2x minus 3y plus 1, that's the f of xy that was mentioned earlier, the function of x and y that's equal to the first derivative. And the initial condition is, the value of y at 1 is equal to 5, right? So this 1 is x sub 0, for the initial x value, and then this 5 is the initial y value, y sub 0 or y naught. And then we're asked to approximate, to 4 decimal place approximation, the value of y, the function that satisfies this at 1.5. when x equals 1.5. Now, as I said, I have done this example. I've had this same example up with the Euler method and improved Euler's method, and if you've seen those two videos, you know the exact solution to this. I have that written here. This is the same as I had in the last video. So this is a linear, non-homogeneous equation in y. You should be able to solve it. Alright, here's the solution curve. Y equals 38/9 times e to the negative 3x plus 3 plus 2/3 x plus 1/9. And then if I plug in 1.5 for x in this function, I'm getting the exact value of the solution at 1.5 is 2.0532162322. It's approximated because I stopped it, but it would go on forever. Alright, so what we're going to do, just as in the previous two videos I made, we're going to use this Rk4 method, right, this Runge-Kutta 4th order method, to approximate, say we didn't know the solution, and we had to use just this here and approximate y at 1.5 and see how close to this 2.0532 whatever we can get. See how close it is when h is equal to 0.1. Alright, so let's get this out of here. I'll bring it back when we find our approximation. Alright, so first, x sub 0 is 1. Y sub 0, the initial y is 5. Then I move a step, right? So I add h to my x sub 0, that gives me x sub 1. Now h is again just 1/10 of a unit, so I'm at 1.1 right now. So hopefully you can see that would take 5 steps, right, to get to 1.5. But like I said earlier, I'm only going to actually do 1 or 2 of these by hand, and you'll see how annoying it is and how tedious it is. And then I'll show you an online calculator for it. Alright, so now the recursion. y1 will be equal to y sub 0 plus h divided by 6, so 0.1 divided by 6 times this quantity here, k1 plus 2k2 plus 2k3 plus k4, where the following are these values of k1 through k4. k1 is the value of f, right, this 2x minus 3y plus 1, at x sub 0, y sub 0. k2 is the value of f at x sub 0 plus half of h, and then y sub 0 plus half of h times k1. k3 is the value of f at x sub 0 plus half of h again, and y sub 0 plus half of h times k2. Right, again, I'm just following along here. And finally, k4 is f of x sub 0 plus h, which is just going to be x1. Right. And then y sub 0 plus h times k3. And just basically writing out all this. Now, let's calculate these, right? In order to find y1, I need to know k1 through k4. Alright, so starting with k1. So k1 is again f at x0, y0. So f at 1, comma 1.1. Oh, sorry, 5. Wow. I put in that one. I was looking at that for some reason. x0, y0. F at 1 and 5. My apologies. So again, the function f here is this 2x minus 3y plus 1. So this is 2 times 1 minus 3 times 5 plus 1. So k1 is negative 12. Right, 2 minus 15 plus 1. Alright, so that's k1. k2 is f at 1 plus half of h, half of 0.1. Well, half of 0.1 is 0.05. And then 5 plus, y0 plus half of 0.1 times negative 12. All right, times k1. So this is f at 1.05, right? Half of 0.1 is again 0.05. And then, 0.05 times negative 12, 5/100ths times negative 12 would be negative 60/100ths, or negative 6/10ths. So 5 minus 6/10ths, 4.4. Alright, and then what is f at this? That'd be 2 times the x times 1.5, right? Minus 3 times the y times 4.4 plus 1. Alright, I know it's probably not that hard, but entering my calculator here, 2 times off to the side, 1.05 minus 3 times 4.4 plus 1. Alright, so negative 10.1 for for K2. Alright, and then K3 is the value of f at 1.05 again, okay, because it's still 1 plus half h, right, x0 plus half h. But then the y coordinate is, y0, 5, plus half h times k2. So 0.05, that's half h, right, times k2 times negative 10.1. And that is 10.1 times 0.05, 4.495. Alright, this is 4.495 here. Okay. Alright, so this is f, so 2 times the x, 2 times 1.05, minus 3 times the y, 4.495, and then plus 1. Again, just entering this off to the side on a pretty basic calculator. So here's K3. Alright, K3 is negative 10.385. And then finally K4 is f at, again, this is x0 plus not half h, but x0 plus h. So 1.1. Right, 1 plus h, 1 plus 0.1. So f at 1.1 for the x. And then y0, 5, plus h times k3. So h is 0.1 times k3 is negative 10.385. And this value here, now 1/10 is this 1.0385. So this is 3.615, I believe. Let me just be doubly sure. Minus 1.0385. 3.9615. Yeah, I forgot the 0 there. Silly me. Alright, so 3.9615. And then we'll calculate this. Right, so this is 2 times the x, right? 2 times 1.1. Minus 3 times the y, 3 times 3.9615, plus 1, and we get our value of K4, which will be the following. Just again, off to the side on a pretty basic calculator, negative 8.6845. Alright, and now that I have K1, negative 12, K2 is negative 10.1, K3, K4, and I know H and Y0, we can now find Y1, which will be the approximation of the solution Y at 1.1. Right. So now Y1 is, h divided by 6, or sorry, y0, so 5, plus h divided by 6, so 0.1 divided by 6, times this quantity, k1, so negative 12, plus 2 times k2, negative 10.1, plus 2 times K3, negative 10.385, and then plus K4, negative 8.6845. Alright, and again, just entering this on a pretty basic, I got a simple TI over here. So I'm just entering all this. 5 plus 0.1 divided by 6 times the quantity, negative 12, minus 2 times 10.1, minus 2 times 10.385, minus 8.6845, close the parentheses, and we're getting 3.972425. Right. And this is approximately the value of the solution curve y at 1.1. All right, and I'll put a little pink box around this. All right, and then I would start over. All right, it's now I have y1, and then I would go on and do y2. Like I said, I think that's where I'm going to stop this. I'll write out what y2 would be equal to. Right, y2 would be equal to y1 plus h over 6 times k1 plus 2k2 plus 2k3 plus k4, where k1 is the value of that f at x1, y1, and k2 is the value of that f at x1 plus half h and y1 plus half h times k1. Right. Sorry about the put it up on screen here. K3 would be f at x1 plus half h, y1 plus half h times k2, and k4 would be the value of f at x1 plus h, which is just x2. Right, and here x2 would be 1.2, right? Because x1 was 1.1, I'd add 0.1, right? My step size was h was 0.1, so x2 is 1.2, and then y1 plus h times k3. And then I'd go again finding k1, k2, k3, k4, put it in here, and then get y2 eventually. And everywhere you see y1, right, that's this value. And remember, x1 was 1.1. Right, so everywhere you see x1, that's 1.1. Everywhere you see y1, that's this 3.972425. And everywhere you see h, that's 0.1. And you see how annoying this would get to write out by hand? So I'm going to say using, do this, using a calculator. Now what I mean by a calculator, I mean an Rk4 calculator. Now if you go to Google, and you can, what I did was I just typed in Rk4 Method Calculator. Rk4 Method Calculator. And a bunch of sites came up. Now some of them had a lot of ads that popped up in the middle of them. I didn't really care for them. I didn't want to show you guys those. But I did find this one site. Let me show you. It's called Maths Tools, M-A-T-H-S tools.com. And you can switch between the standard Rk4 Euler method, improved Euler's method, also called the Hune method or Hune method. But I'm going the standard Rk4 method here. Here I'm putting, I already put all this stuff in for this particular example. So you put in the differential equation, y prime equals 2x minus 3y plus 1. Over here, what's the initial x? 1. What do I want the final x to be? 1.5. Up top, you got the step size h. H is 0.1. And then what's the initial y value over here? The initial y value is 5. All right, y sub 0. Then I hit execute method. Performs calculations and brings up a table where it shows you each step. Now remember just a second ago, right? Remember the value of y at 1.1 we said was approximately 3.972425. That's exactly what I got on my paper earlier. Let me bring that up again. Right, 3.972425 was about y at 1.1, and that's exactly what I'm seeing in this table. So the value of y at 1.2 would be about 3.228436, and we eventually get down to y at 1.5. So again, they're doing this Rk4 method for you, and I would highly recommend just using this. Unless your instructor tells you specifically to do it by hand, I'd say jump to this and write this table out for them, right? Just to show all the steps, write out the entire table. But if you're asked to do it by hand, then you'll have to do it the way I was doing it for that first step, all right, with all the finding K1 through K4 and all that. But using an Rk4 calculator, again at that mathstools.com, the value of y at 1.5 is approximately 2.05 to 4 decimal places, 2.0533. If I round to 4 decimal places. Now let's compare that to the exact value. Remember, at the very beginning of the example, I stated the exact value, right, with the actual solution to the initial value problem, the actual solution curve. And look, that's pretty good. That's better than the improved Euler method was. It's definitely better than the regular Euler method. And this Rk4 method, the Runge-Kutta, classical 4th order method, is used much more often than the Euler methods, because you see how much more accurate it is with even a bigger value, h equals 0.1. Now, of course, if I wanted it to be more accurate, I would use h equals 0.05, 0.01. Just the smaller h is, the more accurate you get. But this is pretty darn good. Right? You see, y at 1.5 is approximately 2.0533 with the Runge-Kutta method, the Rk4 method. The exact value is 2.0532. You're good to the first 3 decimal places, right? 2.053053. That's pretty darn good. Okay. All right. So like I said, I'm just going to write out, I'm just doing this by hand calculation for the one step from 1 to 1.1 here. Again, only if you're truly asked to do it by hand should you really bother doing all this. Because I'd have to do 4 more steps. I'd have to do that 4 more times to get to 1.5, and that would have taken a really, really long time for me to write all that out by hand. All right, so for that first example, great, cool, got it. And then for these last 2 examples I've got for you, I'm just going to jump right to the Rk4 Method Calculator on that mathstools.com. All right, so my next example, and this is another example that I used in the improved Euler method video, where the initial value problem is y prime equals 1 plus y squared, and the initial condition y at 0 equals 0. And again, we're asked to use h equals 0.1. Right? Our step size is just 0.1, but using that Rk4 method, right? That Runge-Kutta 4 method, to approximate the value of y at 0.5. Now, as in the last video on the improved Euler method, we know the exact solution. This is something that's separable. You could pretty easily find the solution to this as y equals the tangent of x, and the tangent of 0.5 radians is 0.546302, blah, 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 right? So there's the exact value of y at 0.5. Now let's see how good this Rk4 method is. All right, so again, I'm just going to enter this differential equation, the initial condition, and I want to end at 0.5, an input of 0.5, and h equals 0.1. So let's go back to that website and back to back to this ODE systems here, ordinary differential equation systems, and then y prime equals 1 plus y to the second power, right, with the caret for a raised to the power. H is 0.1, still using the Rk4 method here. Initial x is 0. I want the final x coordinate, what I'm approximating the solution at 0.5. And the initial y0 is 0, right? And let's execute the method. Performs the calculations here, and so again, 0.1, 0.2, 0.3, 0.4, 0.5. The value of the solution at 0.5 is approximately this number here. And I'll write this down. Right. So turning this off, we get, using the Rk4 calculator, we get y at 0.5 is approximately 0. And looking back at the website, 5463 if I go the first 4 decimal places. And look at that compared to the actual. Same first 4 decimal places. In fact, it's got the same first 6 decimal places. On the computer there, it's 0.546302, and then it's 3 after that, not 4. So it's really good to the first 6 decimal places. That's amazing, especially for h being so big. H is 0.1 here. When we did improved Euler's method, we had to go to h equals 0.05 or smaller to get the first few decimal places, just the first couple. All right, so this Rk4 Runge-Kutta method is definitely more accurate for larger values of h. And that really has something to do with the fact that you're using, you're fitting to a 4th order Taylor polynomial as opposed to just a line, right? It could explain the highly increased accuracy. And that's it for that example. That's all I want to show. Again, you can use the recursion formula, do that crap by hand, but again, I'd have to take 5 steps to go from y of 0 to y of 0.5, and so I mean, just write out this table here, then show whoever this table and say, hey, I had a calculator do the calculations for me. Because doing that by hand, 5 steps or more, is a lot. It would take quite a bit of time, and is very prone to human error. I mean, you copy one little number wrong, or make one little mistake in step 1 or step 3, and it'll throw off the step 5. So I highly recommend finding either this or some other Rk4 numerical solver, numerical calculator. Alright, so I've got one final example. Now the first 2 examples we had exact values for, where we knew the solutions. This one is this is an example that's from the I did this this initial value problem back in the first video on these. I did on just the regular Euler method. And this is a nonlinear differential equation in y, but again, I don't really have a method of solving that'd be nice, So here's one where I don't know the exact value, right, the exact solution curve, but still we can start at our initial condition here, our initial point 0, 0, and through the use of the Runge-Kutta method, approximate the value of the solution curve at x equals 0.5. So again, h equals 0.1, so 5 steps, right, to go from 0 to 0.5, Rk4 method, right, this Rk4 method. So again, you can do the whole recursion thing, where x0, 0, y0, 0, and then do that whole crazy recursion where you're finding all those values of k, and then get to y1, and then do it again to get the y2 to y3 to y4, right, to y5. You know, and then, yeah, that would take, again, a very, very long time for most people. So rather than do all that, I'm going to, again, just pull this Rk4 calculator up. Go here, ODE's system here. The equation this time, y prime equals x plus y to the second, right, y squared. Step size, again, h is 0.1, standard Rk4. X sub 0 is 0. I want to end at 0.5 for x. Y sub 0 is 0. So everything is the same except the equation. And I'll execute method now. And again, 0.1, 0.2, 0.3, 0.4, 0.5. So the value of the solution curve at 0.5 would be approximately 0.1266 if I round that to 4 decimal places. Right. I'm pulling this up. So the value of y, so using the Rk4 calculator, I keep putting RKY, it's Rk4. Using the Rk4 calculator, you know, y at 0.5 is approximately 0.1266. 0.1266. And if you go back, you know, I did that first video on Euler's method, and I'll pull that page up from that first video. Okay, and here it is. It's just popped on your screen. You see the same one, but using Euler's method. Well, actually, that was for y at 0.2. But from Rk4, y at 0.2, I'm looking at my table here from the computer, the website is approximately 0.0200. Whereas y at 0.2 here is only 0.015, which are rounded to 0.2. But this only happened when h was 0.05, right? You needed smaller values of h to get closer to what Rk4 is going to give you at larger values of h. Right. Okay, so probably shouldn't have actually brought that page back up. It wasn't at 0.5 at all. All right. Anyway, so yeah, and highly recommend using some sort of Rk4 method calculator or numerical solver like through mathstools.com to do this, especially if there's more than 2 steps. All right. Now, if there's only 2 steps and your professor or instructor, you know, asks you to do it by hand, that'd be doable. I mean, that wouldn't take that long. You saw me, it took me a little while, a few minutes there, to do 1 step from that first example. So maybe a second step or third possibly wouldn't be too much to ask, but anything more than that would be quite tedious and time consuming. And I would just say, hey, I just used an online calculator. Here's the table, right? And show your professor the table. All right. So hopefully, watching me go over these few examples and showing you that online Rk4 method, Runge-Kutta method. Calculator, numerical solver. Hopefully watching me do all this helps you out when you're working on problems similar to this. All right, and thank you very much for watching.